Okay, so previously we've discussed two methods for solving line integrals. So one of the methods that we could use is we could use the parameterization method. So we have line integral over a curve of f dotted with a displacement. And what we could do is we could take this f and we could take this dr. dr could become the square root of x dot squared plus y dot squared. And then f would become something in terms of some parameterization that we have, which would also dictate what sort of bounds we have. So that really works for a lot of scenarios, but we don't always want to deal with a line integral parameterization. They can be kind of finicky sometimes, like if they're not a line, circle, helix, or other like normal shape that we know. So we can do the parameterization method. We can also do the fundamental theorem of line integrals. So if we have the line integral over a curve C, the gradient of f dotted with dr, then that's equal to the potential function of that gradient evaluated between A and B. And those are also some parameterized points that you might have. But that was very helpful, and that worked in the case of conservative vector fields. Now we have a method that we can use a little bit more universally. It's called Green's theorem. And what it does is it relates the idea of a line integral over to the idea of a double integral or an area integral. So that makes it a little bit easier for us to deal with. So we like to deal with the double integrals and the iterated integrals as opposed to line integrals because we can always deal with a double integral pretty easily, at least at our level where we're using pretty simple functions just for the sake of explaining what something is. Anyways, let's discuss what Green's theorem actually says. So let's say that or partial d, so when I write partial d like that, so if I have just partial d, then that is equal to the boundary of d, right? And then, so that's the boundary of some two-dimensional domain. So in our context, that would be some curve C. So let's say that the boundary of D is piecewise and smooth. So it is continuous, and it can be piecewise too. So let's consider it's piecewise and smooth, and it surrounds some domain D. So what we have here, so we have some domain D in our plane, and we have some boundary partial D, and then we have some domain capital D. So if P and Q, so consider some vector function, f, and that is equal to P as the x component and Q as the y component, and these are both functions of x and y, then what we can do is we can say that the the contour integral around the domain D of P dx plus Q dy is equal to the double integral over the domain of the cross derivative difference, so partial q over partial x minus partial p over partial y. Okay, so you can kind of see where this is coming from. We'll do a proof in a later video, but this is where we kind of go from that line integral idea over here to a double integral idea over here, which makes things just a little bit nicer for us to be dealing with. So let's try an example, a simple example to illustrate the use case of Green's theorem. So find the integral, the contour integral, over the domain of D of x to the fourth dx plus xy dy. And the domain is going to be a triangle with vertices at the origin 1, 0, and 0, 1. So we have 0, 1 here, and we have 1, 0. Oh, wait, no, sorry. This here is 1, 0, and this here is 0, 1. Could have swapped the axes, but that was a really stupid mistake on my part. Anyways, what we have here is then we have this line segment connecting them, and this makes up our curve. So the domain D is in here. So we can say that we're integrating along this closed loop, thus the circle over the line integral. So what we'll do now is we'll plug this into Green's theorem. So if I want to take the contour integral of x to the fourth dx plus xy dy, then I take the double integral of the difference of the cross derivatives with respect to some differential area. So from here, what we should know is that this line is going to be negative x plus 1. With an intercept at 1, an intercept at 1, and our slope is obviously going to be negative 1, so that should be easy enough. So that's one of our lines. We also have y equals 0 and x equals 0 as our lines. So what we can do is we can set up a nice integral here. So we integrate first from 0 to 1 on the x direction, and we can integrate from 0 to 1 minus x on the y direction. Now we got to find our cross terms. So if p is equal to x to the fourth, then the derivative of p with respect to y is 0. So thus dy of p is equal to 0. Now if q is equal to xy, then if I want to differentiate that dxq, well then that's going to be equal to y. So what we have here is we have y minus 0 integrating with respect to y first and then integrating with respect to x. We can carry out that integral and apply the fundamental theorem of calculus. Now what we will get is 1/2 of 1 minus x squared dx, integral between 0 and 1. Again, this should be a very trivial integral to do. What we get is 1/6. Again, just a simple monomial or polynomial integration for you. All right, in the next video, I'd like to cover a more general case of Green's theorem, cover its extensions. This is kind of our last topic dealing with line integrals, and then we're going to be moving on to some important derivatives. It turns out that the gradient operator has a completely different meaning. It has two different meanings when we're dealing with vector fields. We can deal with the divergence of f, or we can deal with the curl of f, so taking the dot product and the cross product of the gradient operator with some vector function or vector field. And then that will allow us to explore more interesting concepts in surface integrals, so applying this idea to surfaces. Then we can cover the capstone Stokes theorems and divergence theorems to round off our course. Thanks for watching. We'll see you in the next one.